Welcome to Free Learning Academy. Let's simplify multi-level feedback queue scheduling. What if the operating system could learn from the behavior of processes and adjust its scheduling strategy on the fly instead of sticking to one fixed rule? That is exactly where multi-level feedback queue scheduling or MLFQ comes into the picture. It is one of the most practical and intelligent CPU scheduling algorithms because it tries to balance fairness, responsiveness, and efficiency all at the same time without requiring prior knowledge about the processes. To understand MLFQ, imagine a situation where different types of processes are running on a system. Some processes are short and interactive, like typing in a text editor or clicking buttons in a browser. Others are long and heavy, like video rendering or large computations. Earlier scheduling algorithms like round robin or priority scheduling treat processes based on fixed rules. But the problem is that the operating system often does not know in advance which process is short and which one is long. MLFQ solves this by observing process behavior dynamically and adjusting priorities accordingly. At its core, MLFQ uses multiple queues, just like multi-level queue scheduling, but with one important difference. In multi-level queue scheduling, processes are permanently assigned to a queue. In MLFQ, processes can move between queues based on their behavior. This is where the feedback part comes in. The system keeps monitoring how a process behaves and then decides whether to promote or demote it. Let us build this step by step with a simple example. Suppose the system has three queues. The top queue has the highest priority and uses a small time quantum. The middle queue has moderate priority and a slightly larger time quantum. And the lowest queue has the least priority with the largest time quantum. When a new process enters the system, it always starts in the highest priority queue. This makes sense because the OS initially assumes that the process might be short and interactive. Now imagine a process arrives and starts executing in the top queue. If it finishes quickly within its time quantum, that is great. The OS considers it a short job and keeps it at a higher priority. But if the process uses up its entire time quantum without finishing, the system assumes that it might be a longer job. So it moves the process down to the next lower queue. This process of moving down is called demotion. Let us take a concrete scenario. Suppose you open a calculator app. It performs quick operations like addition or subtraction and finishes almost instantly. Since it does not consume much CPU time, it stays in the top queue and gets fast responses. Now consider a process like video encoding. It keeps using CPU continuously and does not finish quickly. So it gets pushed down to lower queues over time. This way, long running processes do not block short interactive ones. Another important aspect of MLFQ is preemption. If a new process arrives in a higher priority queue, the currently running process in a lower queue can be interrupted. This ensures that high priority tasks always get immediate attention. For example, if you are running a heavy background task and suddenly click something on your screen, the system immediately shifts focus to your interactive action. This improves responsiveness significantly. Now, one question naturally comes up. What if a process gets stuck in a lower queue forever? This would lead to starvation, which we already discussed earlier. MLFQ handles this using a technique similar to aging. After a certain period, processes in lower queues are moved back to higher queues. This ensures that every process eventually gets a fair chance to execute. Let us visualize this with a simple flow. A process starts at the top queue. If it behaves like a short job, it stays there. If it behaves like a long job, it moves down. If it waits too long in a lower queue, it gets promoted again. So there is continuous movement based on feedback. This dynamic adjustment is what makes MLFQ powerful. Another interesting feature is that different queues can use different scheduling algorithms. Typically, higher priority queues use round robin with small time slices for quick response, while lower queues may use larger time slices or even FCFS for efficiency. This combination allows MLFQ to handle both interactive and batch processes effectively. To make this even clearer, imagine a real life analogy. Think of a customer service system in a bank. New customers are initially served at a fast counter. If their work is simple, they finish quickly and leave. If their work is complex, they are redirected to another counter that handles longer tasks. But if someone has been waiting too long, they may be moved back to a faster counter to ensure fairness. This dynamic handling is very similar to MLFQ. Now, why is MLFQ considered better than many other algorithms? The biggest reason is that it does not require prior knowledge about processes. Algorithms like shortest job first assume that we know the execution time in advance, which is not practical. MLFQ learns from actual execution behavior. It adapts automatically, making it suitable for real world systems. However, MLFQ is not perfect. It is more complex to implement compared to simpler algorithms like FCFS or round robin. The system designer has to decide the number of queues, time quantum for each queue, and rules for promotion and demotion. If these parameters are not chosen carefully, performance may suffer. But when tuned properly, MLFQ gives an excellent balance between responsiveness and throughput. In modern operating systems, variations of MLFQ are widely used because they can handle mixed workloads efficiently. Interactive applications get quick responses, while long running tasks still make progress in the background. So, if we look at the bigger picture, multi-level feedback queue scheduling is like a smart decision maker inside the operating system. Instead of following fixed rules, it observes, learns, and adapts. It ensures that short tasks get quick service, long tasks do not block the system, and no process is left behind indefinitely. And that is what makes MLFQ one of the most practical and intelligent scheduling techniques in operating systems. That is it for this video. See you in the next one.